Okay, things are about to get really exciting in chapter 18. We are going to talk about galvanic cells. So before we actually talk about a galvanic cell, we're going to talk about a reaction that I would love to do with you, but we're not in the same room right now. So if we were together, I would put some solid zinc, just like a chunk of zinc metal, in a solution that contained copper 2+ ions. And so let me draw a picture of what that would look like. Let's say that I had a beaker. I'm going to do this in a beaker. I would probably do it in a test tube, but it's easier to draw a beaker. So here's my beaker, and I'm going to put down here, I'm going to put my chunk of zinc. And zinc, it just kind of looks like, it's like a rock, sort of. And it's this gray color, so I'm going to color it gray. Colored right over the top of my zinc. There we go. And then the copper 2+ solution is kind of like this teal color, like that. So those are the copper 2+ ions in there. And this is in water, and there's an anion in there too, like maybe sulfate, something that's not something that is not reactive, so it's like a spectator. I'm going to draw a copper 2+ ion hanging out in this solution. And so if you put these two things together, they will react. They do a redox reaction. And the redox reaction that they do is the zinc atoms will transfer electrons up to the copper ions. Each zinc atom will transfer 2 electrons to a copper ion. And so that is going to be zinc reacting with copper 2+, and the zinc, as I said, is going to be transferring 2 electrons to the copper. So that means that the zinc is going to go from zinc metal to a zinc 2+ cation. And the copper, when it absorbs those electrons, is going to just become copper, the atom. It's not going to be an ion anymore. And so as this is happening, the zinc and the copper change their state. So as the zinc loses its electrons, gives up its electrons, and becomes zinc ions, the zinc, let me draw it down here again, the zinc just starts crumbling. Like it just starts falling apart and breaking up into little tiny pieces until we can't see it anymore because it's broken up into such tiny pieces that our eyes can't even detect it anymore. And that zinc is now floating up here in solution as zinc ions. Also, at the same time, all of that, I'm going to erase this for a second, we had all of that copper 2+ ion floating around in solution, beautiful. As that copper picks up the electrons and becomes the copper atom, it also starts removing itself from solution, but it doesn't disappear. It actually solidifies and becomes metallic copper, which is kind of this like reddish brown color. It's more like this color right here. And that's can't see that. That's the copper, really can't see that. Nobody can see any of that. This is the copper. And up here in the solution, remember this is where we have the zinc now floating around. And it is totally colorless. Like there's just no color to it at all. So maybe I shouldn't draw it gray. I should just no color for the zinc. So we see this with our eyes. We can see this awesome exchange where the blue copper ions are turning into a reddish brown copper solid, and that metallic grayish zinc solid chunk is just, to our eyes, it looks like it's disappearing. It's not actually disappearing. It's just becoming an aqueous ion that we can't see anymore. This reaction, if we're just doing it at room temperature, this reaction would take maybe 20 minutes, maybe 30 minutes, kind of depends on the strength of the solution. But if we heated it up, it would happen really fast, just in a couple of minutes. So this is a really awesome example of a redox reaction taking place like right in front of our eyes. So let's talk then about the galvanic cell concept. So when you put the zinc and the copper in direct contact with each other, which is what we have right here. When you put them in direct contact with each other, these electrons are spontaneous in the sense that they want to move. So they just spontaneously want to move from the zinc to the copper. They're more than happy to do it. And so if what we do is separate the zinc from the copper, if we physically separate, so they're not touching anymore, separate the zinc metal from the copper ions. If they're physically separate from each other, then they can't just pass electrons from the zinc to the copper because they're not in contact with each other. But if we connect them with a wire, the electrons can travel down the wire They move from the zinc to the copper. And as the electrons are traveling down the wire, some of you know what this means. This is how we generate electricity. This is what we call a galvanic cell. Galvanic cell used to be called the voltaic cell. So you could hear it called either one of those things. So this is what a galvanic cell is going to look like. So remember, what we want to do is physically separate the two components. We want to physically separate the zinc metal and the copper solution. So we need 2 beakers instead of 1 because we don't want to put them in the same beaker anymore. We want them to be physically separated from each other. So we're going to put the zinc in the beaker on the left. And we're not going to put just like a rock of zinc in there. We're going to get smart about this. We're going to get like a strip or a small rod, like maybe a nail type thing. We're going to get a strip of zinc. The reason that we're going to use a strip is because it's going to be easier for us to clip a wire to it. It's thin. It's hard to clip a wire to a rock. So this is our zinc solid metal. And here's my beautiful beaker. So that's one component. And then over in the other beaker, remember our other component is our copper. So over here, in this side, we're going to put our copper ion solution. Like that. Now, remember I said what we need to do is connect the zinc to the copper with a wire. So here's the wire. But how do you connect a liquid to a wire? Like, how do you physically connect a solution to a wire? I mean, you can't really do that because it's not an actual object. So we need to have something for this wire to connect to, and then we can dip that object down into the solution. So that's how we're going to connect to the copper. We're not going to clip the wire to the copper solution. We're going to clip the wire to some sort of conductive metal and then dip that conductive metal down into the solution. And the perfect thing for us to use as the substance to clip our wire to is a piece of copper metal, because it's the same type of atom as what's in this solution. And also, we're going to find you already know, it's a product of the reaction. So it's not like we're introducing some kind of new random thing in there. So this is going to be a piece of copper solid. And then here is our wire that's attaching these two metals. So this is amazing stuff. Now, remember, over on the other beaker, the zinc beaker, as the reaction proceeds, this creates zinc solution, zinc 2+ ions in solution. So we do want to have some liquid in here as well, so we have a place for those ions to go. So this is going to be a zinc 2+ solution. And it doesn't have to start out as a zinc 2+ solution, but we're going to eventually make it, so we're going to put some water or something conductive in there to begin with. And we need to have an anion because Mother Nature doesn't let us just put cations in beakers. So maybe we have chloride ions running around in here as our counter ion, so everything stays nice and balanced. So we're just going to pick some kind of ion that's inert, not reactive, is not going to interfere with this at all. So this is the basics of the galvanic cell. So remember, still, our motivation, the electron's motivation, is to move from the zinc this way down the path. The electrons are moving from the zinc down the path to the copper. And we can actually interrupt this electron flow whatever way we want. We could plug a voltmeter in and we could measure however many volts we're passing through. We could do something more interesting than that. We could maybe connect a little LED light bulb type of a thing to it and light the light bulb up with the electricity that's moving through. So we could do something to prove to ourselves that the electrons were flowing. That's like the world's worst light bulb. Let's turn it back to a voltmeter because that looks better. Now, one of the problems that we're going to have with this galvanic cell is that as our electrons are moving from the zinc side over to the copper side, if we're not careful, we have the potential to build up an excessive amount of electrons on the right side of the right beaker, the right half of this cell. And is that even an option? Would Mother Nature allow us to accumulate a whole just crap ton of electrons free floating over on one side of the cell? And you might be able to guess that no, that's not going to happen. We cannot, just like we can't have positive charged copper ions running around without something to balance them, we also can't have electrons being accumulated on one side of the cell unbalanced. So what we need to do to equalize this is to create what we call a bridge that connects the two cells again. So this is what we call a bridge. We call it technically a salt bridge. The salt bridge is not used for any sort of electricity conducting, none of that type of stuff. The salt bridge is just used to help prevent the accumulation of negative charge over on the copper side of this cell. The salt bridge is made up of some sort of inert, non-reactive, neutral, ionic compound, like KCl would be a great choice. And as this reaction, this redox reaction takes place, potassium ions and chloride ions from the KCl are free to migrate through the salt bridge and actually down into the solutions to help keep everything charge balanced. So in this particular setup, where we have electrons that are heading over to the right side, we have the potential to be building up negative charge over on the right side. Our potassium ions from the salt bridge are going to be migrating down into this solution to help balance out the negative charge of the electrons. Likewise, over here on the left side, because this side is losing electrons, it's losing negative charge, the salt bridge has these chloride ions that can migrate down into the solution and help replace the negative charge as it's being removed. So this helps everything to stay charge balanced and allows the reaction to continue to proceed. Last couple things that I'm going to talk about are just some of the names of the different features of the galvanic cell. So on the left side of what we've drawn here, the left side of this is the oxidation side, the oxidation half reaction. And I know that this is the oxidation side because of oil rig. Oxidation is lost and the electrons are leaving the zinc side, the left side. The electrons are being lost from the zinc. And the right side of this is the reduction half reaction, which I know oil rig, reduction is gain. So the electrons on this side are being gained by not the copper metal, but the copper 2+ ions. They're being picked up by that. These strips of metal that we're using inside this galvanic cell are called electrodes. So both of them are electrodes. And the electrode where oxidation is occurring is called the anode. You may have heard the term anode before, and that's what it means. The anode is the electrode in the oxidation half of the redox reaction. And on the other side, the electrode is called the cathode, which is also a word that you may have heard before. Cathode is the electrode in the reduction half reaction. And the way that I remember which is which one is the anode and which one is the cathode, is that I remember red cat. This is my kitty cat, and my cat is red. And oh man, this is a really good cat. It's a happy cat. It's got whiskers. Red cat helps you remember reduction has the cathode electrode and oxidation has the anode electrode. Red cat, reduction happens at the cathode.